All right, so on the next page here, we're going to take a look at another theorem that's going to help us understand something very special and unique about alternating series. And here's actually what it says. Okay? It says, let's suppose that I have an alternating series. Okay? Maybe it looks like this. Maybe it's an alternating series, -1 to the n minus 1. It's multiplied by some a sub n thing. And let's suppose that this turns into some value s, right? S is the grand total sum of that addition problem. And let's also suppose that all the conditions for like that alternating series test are met. So we'll say that a sub n plus 1 is less than or equal to a sub n for all n, and the limit of a sub n as n approaches infinity is equal to 0. Okay? So if I have all of these particular things, then I can actually reach the following really powerful conclusion. So essentially, if I have alternating series test applying and I know there's an answer, even if I don't know what the answer to that series is, even if I don't know the value of s, but I know it exists, then I can state this. If I do s minus s sub n, so notice what this is saying here is I'm going to find the difference between the grand total addition and just the running total up to some point. So like imagine that I added the first 10 terms out of an alternating series. That would be S number 10 in green. And that might be getting closer to the grand total sum of S, but it might be, there might still be some gap between them because I haven't added everything yet. And so what this is going to do is this is going to measure that gap. How far away is my partial sum from the actual sum? Now, I might be overshooting or undershooting the actual sum at that point, and I don't really care. That's why I'm going to put the absolute value bars here. I just want to know how far away am I from the total sum thus far. And here's the cool thing. We'll be able to guarantee that that distance, how far away we are, is automatically going to be less than the n plus first term of the series. Okay, this is really weird and can be really, really awkward to try to understand. I'm going to go ahead here really quickly and try to at least sketch out an intuitive picture to help us understand maybe what's happening. So take a look down here. I'm going to sketch out a quick number line. Let's imagine that this is a number line that's keeping track of our running total of the addition problem. So that would mean that automatically at the start, we're going to imagine that we start at 0. And based on whether we're adding stuff or subtracting stuff, we'll be able to kind of see where the grand total is. Okay, so let's suppose that I'm able to suppose the following. Let's say that I'm going to start by adding the first item into the addition problem. So I'm going to go ahead and put this vertical bar up here and then illustrate what happens when I begin to add these different things. So let's suppose that I add a bunch and I land all the way over here. Okay, so this over here would be S number 1. This is my running total so far. And this is after I've added the first thing from my list. So when I add the first thing into my addition problem, I make a big jump forward. Okay, because my first thing here, you'll notice, is positive by the way I've defined it. Then the next thing over here is going to be negative, right? Because my second term here should be some negative amount. So when I add that value in, my sum's actually going to go down a little bit. So maybe it goes down here. And this is A2, and it takes me backwards. Now my running total has decreased because I had to subtract something. The series is alternating. Well, what I'll notice is, again, I have to make sure that a sub n plus 1, the next thing I add, is a smaller amount than the thing previously. So if my first arrow is very long, my second arrow's got to be shorter. And my next arrow is also going to have to be shorter, but it would be an arrow that has to go up. So maybe it takes me back over to here, and this lands me at S number 3. This is after I've added 3 things. So this is A number 3. What I could start to see is that I'm probably going to have some sort of whittling down process where I go over and back and over and back and over and back and over and back. And I'm going to kind of slowly kind of like ping pong down to some final point. And maybe this is where S is sitting, right here in the middle. Okay? Maybe it doesn't seem too hard to imagine that. The cool thing, though, is now I can actually see exactly this inequality shaping up. you can actually visualize in this picture down below the gap between any S, or sorry, between the black S and any green S sub n. For example, let's take a look here at S minus S1. You can figure out how big that gap is. Maybe it's 2 units long, or it's 10 units long, who knows? Distance is there. Wouldn't you agree that if I'm working with S number 1, according to the theorem, if I look at A number 1 plus 1, I look at A number 2, compare this gap down here in blue to this gap created by A2. And you'll notice the A2 gap is larger. You can see the same thing if you were to say do something like S to S2. That gap should be smaller than the gap created by, or the distance created by A3. Right? And I can kind of see this playing around in the picture. And if I kept drawing more, I could see this sort of behavior happening. So this is a really powerful theorem, but what it allows us to do is to make some really important and impressive approximations about the actual sum of the series. Let's take a look down here at example number 4 to kind of see how this works. Again, we're going to look at the alternating harmonic. Now, the first part here is very simple. I just want to know, what is the 7th partial sum of this series? Well, again, if I know this starts with the number 1 over 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh, I could easily just add all these numbers together. Now, for the sake of simplicity in the video, I'll just tell you that this is 319 out of 420. Okay, you could double check me on that if you're unsure, but ultimately this comes out to be roughly 0.7595. Okay, that's like a rough approximation of what I have. So I might be interested in, does this particular series add up to anything? And as I'm looking at the running totals, I can start to see like, okay, you know, we're kind of maybe getting closer to something like 0.75, maybe something closer to 1, you know, who knows? It kind of depends on what we're narrowing in on slowly. We kind of expect to have this kind of ping-ponging behavior where we kind of slowly whittle in on a value of S. Now, we already saw previously by alternating series test that this series actually does converge. But I could now ask the following question. If I know this series converges and there is a capital S, how far away S7 from the actual right answer? Like right now I'm at about 0.7595. Is that like 1 unit away from the correct sum? Is that like 3 units away? Is it like half a unit away? Like how close is our answer to the right answer thus far? Well, the above theorem tells us exactly what to do with that. It'll help us find this upper bound on how far off the number is that we calculated in A from the actual sum of the series. So I'll state this. By the theorem above, we know that whatever S is, when I subtract S number 7 from it, that should automatically be less than or equal to A sub 7 plus 1, or A sub 8. Now, if I go back to my series up here, I should be able to determine what A sub n actually is. Remember, that's the portion of the series that doesn't actually have the negative on it. So this would here still just be 1 over n, which means that the thing number 8 in that list should be 1/8, or as a decimal, that's 0.125. So this is actually an incredible conclusion. Take a look at what we can say. We could argue this. So we know that 319 out of 420 is at most 1/8 or 0.125 units away from the actual sum of the series. So this value, like this 0.7595, is like pretty freaking close to the right answer. It's only off maybe by 1/8. I oftentimes like to think about kind of making like a little picture I'm never going to ask you to make this picture, so this isn't part of the objectives for the course, but I like to kind of almost imagine that 1/8 or this 0.125 is like an amount that I could like jump up or jump down, and I can kind of make like a little window here. And I could say that I feel like, or not that I feel confident, but that I'm completely confident that the real value of S is kind of somewhere between those endpoints. So you could imagine adding like 0.125 to this value. So you know that like somewhere between, I don't know, like 0.87, 0.88, and maybe what would the subtraction look like? 0.63-ish, somewhere around there. Like, you know, the value sits in there. You know it. It's not a guess, it's a guarantee. That's pretty powerful. So even without knowing what the sum of the series is, we can kind of know where it lives, right? There's no way the sum of this series comes out to be 16. It's not possible because it doesn't fit inside the bounds. We can also take a look here at something like part C, where we can reverse the question. We might ask, what is the first partial sum of the series? Where we can guarantee that it would be within 1/1000th of the actual sum. Okay, well, if I think about what that means that we want to have S minus our S sub n. We're not really sure what that n value is going to be yet, but we'd like this, which we know is less than a sub n plus 1. We want all of that to be less than 1/1000th. So what I can do is I can just imagine, well, how about I make this less than 1/1000th? Then I would definitely be able to say that I'm able to guarantee that the absolute value on this side is definitely less than 1/1000th. So the question would be like, what would I have to pick for n to make this possible? Well, the cool thing is I can actually kind of work right from here. So I can say that this is what we need to ultimately solve. So I can see here that we solve 1 over n plus 1. That is the number in spot n plus 1. I want that to be less than 1/1000th. And if I try to think about when that happens, if I multiply 1,000 to both sides and n plus 1 to both sides, I can see that I need n to be greater than 999. Okay, so this actually seems fantastic. If n is greater than 999, then I'll get all of this to be within 1/1000th. So the first partial sum of the series that I could actually use then would look like this. I could say the first partial sum we would need is S sub 1000. That would guarantee that I'm less than 1,000. Notice if I wanted to be like equal to 1,000, then I could probably have used 999 because I would have had a less than or equal to on here. And I think in my notes, that's what I had kind of written out originally, is that what would happen if I wanted this to potentially be equal. But if I want it to be less, then I would have to do something like this. So this is cool. Notice that I could kind of then almost predict ahead of time how many items I need from this addition problem to add together so that I can reach the desired accuracy. I could say, I want to be within 1/1 trillionth of the actual sum. And this can help me compute how far off do I need to be. Down here, I'll be able to show something kind of extremely surprising, that actually, later on in this course, we'll be able to prove that the sum of this series, this alternating harmonic, is actually the natural log of 2. Now, the cool thing here is that if you were to type natural log of 2 into a calculator, I bet you could guarantee it's definitely one of the numbers that falls inside that interval we previously constructed. Okay, in the next video, we'll take a look at some final definitions for this section, some new other key pieces of terminology, and try to highlight why these pieces of terminology are so important.